All right, so I just have a few slides here introducing some of the work that I do. I do a combination of laboratory work and field work, and also some computational work that's a little bit less of what we do right now. But here are some, just images of, from the past few years of cool things that we've done, including, cruise on a research vessel to collect seismic data. You're working with some nanoparticles and some other cool stuff. So let me continue on here. So right now, my research focuses on four different areas. We are looking at gas hydrates, both as kind of a resource and also kind of on the scientific side as a geohazard and looking at their role in the global carbon cycle. We have some work on nanotechnology right now, using nanoparticles to stabilize foams and also to treat produced water to remove oil from it. I do fundamental petrophysical research, including a lot of use of nuclear magnetic resonance, for characterizing the pore system of rocks, and also looking at different multi-phase flow properties of rocks. And then we're getting more into decarbonization, as are many people. And this includes some work on subsurface hydrogen storage, and then a new research initiative on carbon management that we're trying to get going. So here's some examples of what we do with gas hydrates. So for those of you who don't know, gas hydrates are these ice-like compounds. They're made of water molecules that are arranged around a low molecular weight gas molecule. We call it a guest molecule. And the most abundant naturally occurring ones have methane as their guest molecule. So they form these hydrates that look like ice, but you can light it on fire, which is pretty cool. And if we look at the global resource potential, this is called the hydrate resource pyramid. We're looking at how much gas in place we think there are in gas hydrates around the world. And, when you look at these numbers, it's, many, thousands of trillions of cubic feet of methane potentially recoverable. So there's a lot of work around the world being done to understand those. A lot of my work focuses on characterizing gas emissions from naturally occurring gas hydrates. So here's an example of some methane bubbles coming out of the seafloor, which may or may not be from hydrates. But we've done some work. This is an example from offshore Svalbard up in the Arctic. I actually have a student leaving today to go on a research cruise up there for a couple of weeks with some colleagues at a Norwegian university. But really understanding, how these gas chimneys form the sediment and how they lead to these, bubble columns that we can detect in the water, and how it's related to, the presence of hydrate and gas and fractures. Here's an example of some seismic data we collected offshore North Carolina, looking at, where there's hydrate, where there's gas. Here's a salt diapir, so understanding the whole dynamic hydrate system there. I took two graduate students and an undergraduate out with me for a 32-day research cruise on the Marcus G. Langseth, which is pictured here, where we collected cores and seismic. So we have a lot of fun doing this. It's a really cool area, and so a lot of kind of wide open science questions still remain.
I am still upset that I couldn't go.
Yeah, next time. I may be sending somebody out again this summer. I don't think I'm going, but we may have another opportunity to go back out. On the nanotechnology side, so nanoparticles are really cool. They're very small and they have a very high surface area. And these are some images of some of the silica nanoparticles we work with there. You can see this is a 40 nanometer scale bar. So we have a nice transmission electron microscope here at the Texas Materials Institute that we can use to take really cool pictures of very small things. What we do is we graft various organic polymers onto the surface of these nanoparticles to modify the surface chemistry, and that allows us to do all kinds of cool things. For example, we can stabilize emulsions with them. We've done a lot of work understanding how the emulsions get stabilized and how the surface chemistry of the nanoparticles allows them to remain stable. We've worked on stabilizing foams. So these are CO2 foams at high pressure, high temperature, high salinity. using different types of surface coating. I think in this case, we were using a tertiary amine surface coating. So a lot of really cool stuff we can do. This has applications for enhanced oil recovery, but also for carbon storage. If you inject the carbon dioxide as a foam, you actually get much better utilization of the pore space than you do otherwise. And then we currently have some ongoing work with an industry partner right now where we're using magnetic nanoparticles that we get to attach to the surface of oil droplets in produced water, and then we can remove them using a magnet. So this is a way of cleaning up that last little bit of oil that's in the produced water that you can't get at using gravity separation or centrifuging or anything like that. We've also looked at using these types of particles to remove things like lead and other heavy metals from water. So it's definitely got a lot of applications in these magnetic nanoparticles. Dr. Pradanovic and I have worked on these for several different applications, and they're really cool things. You can also get them to heat up if you expose them to an oscillating magnetic field. And so
magnets are fun and bubbles are fun. So when you put the two together, oh my.
That's right. What's not to like?
Right.
Yeah. And I actually want to show you all a video. This is us using these nanoparticles to separate. Let's see. I need to turn my pointer back to my pointer. Here we go. This is using the nanoparticles to separate oil and water. So you can see we're mixing oil and water over here. Now we're going to add some nanoparticles to it, and then we'll mix them a bit. I'm going to skip forward because this is a little long. All right, keep mixing. You're doing great. Okay, and then we turn on the pump and we run them through this magnetized battery of, this is steel wool that's in these tubes. And the magnetized steel wool picks up the oil droplets, and what comes out on the other end is clean water. And so we're able to remove like 99.7% of the oil droplets that are there. So it's pretty cool stuff. Okay, we also do some work with basic petrophysics. A lot of my work right now is focused on understanding gas flow in sediments. This has applications both for gas hydrates, but also for carbon sequestration. So we've done some, this is numerical simulations of, immiscible displacement. So understanding, the percolation properties and looking at, how fracturing happens in shallow marine sediments. But we also do things like with nuclear magnetic resonance. This is some fluid typing work. This is a method that we developed using a Gaussian clustering algorithm to take this two-dimensional NMR data and break it into different fluid populations. We also do work looking at micropores and shales. And this was a nuclear waste storage project that I worked on for a little bit. And finally, we are more recently getting into decarbonization. This is obviously a big and important area. And so we've done work on looking at subsurface hydrogen storage. So all the different processes involved here, including microbial activity, the use of a cushion gas, different injection schemes, and then also some work that we're getting underway on carbon management. So understanding the entire kind of supply chain of CO2. When you capture it, you move it around, and then you sequester it somewhere. So how do we optimize that system as a whole engineered system? So I'm going to stop there.